So let's understand map phase or map task. So this is what happens in a map phase. First, let's consider one block or one split which is of size 128 MB. Now, obviously, your data size would not be so small. It would be multi GB, hundreds of GBs, or maybe in terabytes also. So if let's say the size is 100 GB, then the number of blocks would be 100 GB divided by 128 MB. And the process that I'm discussing would be same for all the blocks. And what would happen is that the map phase would run multiple tasks in parallel depending on the number of cores or the number of CPUs that you have in the machine. So let's say if there are 4 cores, which is very less by the way, then this process would run parallelly for 4 blocks. If there are 8 cores, the same process would run for 8 blocks, and so on. If the file size is pretty big, then the remaining blocks would wait for its turn to be processed when the CPU becomes available. Alright, so what happens is that a single block contains multiple records, right? That I shown you in the HDFS slide. So let's say for simplicity's sake, this particular block has only 5 records with certain key and certain values. Now what is this key for each individual records? Now let's take an example, right? So let's say there's a order management system and the file is for multiple orders. We have order ID, the price of the order, the items of the order date and the delivery date, etc. So what do you think the key would be? So in this case, the key would be order ID. Now let's say you have a customer file. So wherein you have customer ID, customer name, email, address, etc. So the key would be customer ID, right? So that's what key is. From the examples that I have given, it seems like key would be always unique in nature, meaning that the keys would have unique values always. That is not the case. So let's take another example, again the order management system. So let's say you want to generate a report wherein you want to find out the number of orders state-wise or country-wise. How do you find that out? You want to find out total number of count per state or per country. Let's say Toyota Motors, which has operations across almost all the countries in the world. Now Toyota Motors want to find out the volume of sale across all the countries because it wants to do some inventory management, or maybe it wants to change the supply chain. In that case, what would be the key? Will the vehicle ID be the key? The answer is no, because the requirement is to find out the volumes per country. So in this case, the countries would be the key, or the country column would be the key. So it does not necessarily mean that unique record would be the key. The key can be anything depending on the requirements for which you are running the map reduce job. Okay, now what does map do? What is meant by map? What map does is it reads each and every record one by one, and then we write the transformation logic on top of these records. So let's say this is the transformation logic that we write, and what map does, it reads all the records one by one, and the user written transformation logic is applied on these records again one by one. We do not have to run any loop, we do not have to specify any loop. It is done by the framework itself, the map phase itself, or the map task itself, that it will read the file or read the block, and then it will read all the records one by one, and whatever logic we mentioned in the map code, that logic would be applied to all the records. Now after applying the logic, it would emit same number of records, more number of records, or less number of records. Why 3 different cases? Because let's say you have multiple columns and you are selecting only a few columns. In that case, the input number of records and output number of records would be the same. Let's say you have another scenario like the country that I told you, sales volume per country. In that case, you want to filter based on country. So if you are filtering, then you are reducing the number of records. So in that case, the input number of records would be more than the number of output records. And when the number of output records would be more, let's say you have this order management system, and in a single row for a particular customer, all the product items is mentioned in a single column. But that is not a good way to handle or model data. So what you want to do is that you want to create multiple number of rows depending on the product items which is there in the order. So in that case, the number of output records would be more than the number of input records. So the map phase applies the transformation logic which is written by the user on each rows and emits either same or less or more number of records. Now, after emitting these records, the same records would be written in memory and in the same order that it reads. For example, in this case, we have record 1 which contains key 2 and value 2, record 2 contains key 4 and value 4, record 3 contains key 3 and value 3, but record 4 contains key 1 and value 1. So does record 5. So while writing in the memory, first it would write in the same order in which the rows were read. And then after that, there is a background thread which is running. And this is also a program which is part of the framework itself. What it would do, it would read these keys and sort them in memory and put them in a sorted order in memory. If you see, it has key 1 first, then key 2 or K2, then K3 and K4. I have not shown all the 5 records, but you get the gist. So the records would be sorted in memory itself by the thread that is running. And this is called sorting. So the keys would be sorted in memory, right? Now after that, obviously memory is not unlimited. We do not get infinite amount of memory. Let's say the size of the files are few hundred GBs. It is highly unlikely that the amount of RAM or the amount of memory that will be available in the server would be of that scale. So memory would be always much lesser than the disk size. Now in that case, what would happen? The thread would read the records from memory and it would pass to another program called partitioner, and then it would partition based on the keys. So it would read the sorted records and then partition it and put the records in a sorted fashion in these individual partitions. And as I said, the records would be read from memory and it would be sent to a program called partitioner, and these partitions would be written to disk. Now, why it has to partition? We'll come back to that later on. The partitioning would be done based on the keys, which will be done by the partitioner program. Now, after the map task runs for all the blocks, we'll have a lot of small files. We'll have a lot of small files written to disk, which are individual partitions. So what map would do, or what the map phase would do, it would merge these partitions in a large single file. Now here I have 2 partitions. That's why I'm showing you only a single file with 2 different blocks, but you can imagine that it would be a large file with all the partitions merged. Now one interesting part here is that except for this transformation logic, which would be written by us, everything else is handled by the framework. We do not have to worry about reading the records or writing the records in memory. We do not have to worry about sorting the records in memory, or for that matter, partitioning the records also. Even the merging in the file is handled by the framework. So the MapReduce framework would contain multiple programs and tools which will do all these tasks for us, and we only have to worry about the transformation logic or the business logic. Because if you think about it, all these tasks, right, like reading from files, writing to memory, sorting based on key, writing to disks, these are all infrastructural work and these are all repetitive work. So what the MapReduce framework does, it has written codes which is part of the framework, and those codes or those programs will do all the work like reading from the file, writing to memory, partitioning, and then merging the records, etc. But the framework has no idea about the business logic. It would never know what is the, or what columns you want to select, what functions you want to apply. It can be date function, it can be type conversion function, etc. Or what filter for that matter you want to apply, because these are part of business logic. So that's why we developers only write the transformation logic and everything else is handled by the framework. And this map phase is called as map task, mapper, or map partitions. Now why map partitions? Because if you think about it, there are multiple partitions and the map phase would run on all those partitions. And what would map do? It would read individual records, apply the business transformation logic which is written by user, and then it will do the remaining tasks like putting it in memory, sorting it in memory, writing it to disk based on partitions, and then merging the records in a larger file. So that's why this entire map phase is also called as map partitions or mapper or map task. And one more important call out is that the map phase or the mapper will never do any summation or aggregation or anything of that sort. That is not the job of map phase. So it will only read the records and emit similar, less or more number of records. For example, select statement, which is selecting records, where statement, which is filter expression. I'm taking cues for SQL, but you can imagine select is selecting the columns, where is actually filter. Then we have functions like converting the data type, which is cast function in SQL, then converting the data type to date or doing some date operations, which is date function in SQL, etc. Now, as user, we have to write this logic. We'll have to write this transformation logic in the function here. So these are the things that are done by the map phase. It reads the records, applies the transformation logic, and emits the same number of records or more number of records or less number of records, and then the remaining tasks. As you can see, there is no sum, grouping, averaging, etc. That is not done by the map phase. That is done by reduce phase. Now, after this map phase is complete, it goes to the reduce phase. Now, let's say we have multiple nodes. We have, let's say, 3 nodes. The first one is node 1 or map node 1, then map node 2, then map node 3. It's not that we'll have separate nodes for maps and separate nodes for reduce. What I'm trying to show you here is that these are the nodes where the map tasks run or map task got executed. Now in map phase, eventually the final output was the merged files, right, based on the partitions. So let's say map node 1 has 4 partitions, and this is the first merged file and this is the second merged file. In map node 2 also we have 4 partitions, and these two are the merged files. Same is the case with map node 3. So these are the files which are the final output from the map phase. And these files are sorted based on keys and all partitioned based on key ranges. Then let's say we have these reduce nodes. Now again, don't get confused, because maybe map and reduce are running on the same node or maybe on different nodes. It can be any scenario. Now what this reduce node would do, based on these partitions, as we have 4 partitions, that's why we have 4 reduce nodes. Each partitions would go to individual reduce node. For example, the red partition would go to the reduce node, blue partition might go to reduce node 2, black partition might go to reduce node 3, and gray partition might go to reduce node 4. One thing is that keys with the same value will always land on the same reduce node, and keys with a certain range would always land on the same reduce node. So now what has happened, the output of the map phase, which are the sorted, partitioned and merged file, the partitions were copied to the reduce nodes based on the key, and each reduce node has its own set of keys. And this phase is called copy phase, wherein the framework copies these partitions to their corresponding reduce nodes. So the different partitions from the map phase have been copied to different reduce nodes. Now the framework would run threads which will read these individual files or individual partitions and then merge them and sort them based on the value of the keys. Right, so this is also done by the framework, which will read these individual partitions and then sort and merge them together. Now notice that these 6 partitions are coming from 3 different map nodes. These 6 different blue partitions are coming from 3 different map nodes, because 2 blue partitions are here in the map node 1, 2 blue partitions are in map node 2, and 2 blue partitions are in map node 3. So all the same partitions or all the same block with the same key or a certain set of key range have been copied to individual reduce nodes. Now that's why these files are scattered across in the reduce nodes also, because these are getting copied from different map nodes. And one more thing that you notice, that the number of map nodes are different than the number of reduce nodes. It might not be the case always, but in most of the scenarios, the reduced nodes or the number of reduced nodes would be much higher than the number of map nodes. And as part of the reduced node, the first job of the framework is to merge these different splits coming from different map nodes to a single sorted file. And once it is done, then the aggregate function, which is written by the user, is applied on all the records collectively. Because this is an aggregate function which is written by us, those aggregate functions or whatever logic we mention in the aggregate function would be applied on the entire sorted file. Obviously in a record by record basis, and let's say we are doing a grouping, or we are trying to find out average or sorting, etc., or joins, that would be done by individual sorted files. Now here as well, this is the only portion where developers would write code. Everything else would be handled by the framework, like the copying the splits or the partitions from map nodes to their corresponding reduced nodes, then merging these partitions into a single sorted file. All these would be taken care of by the framework, and on these records, the aggregate function that we write, which is a business logic, would be applied. And eventually the records would be written to a distributed storage like HDFS or AWS S3 or Google Cloud Storage. So this is on a very high level what the map phase does and the reduce phase does. The purpose of map phase is to read records one by one and apply the transformation logic which is written by user on those individual records. And the purpose of reduce node is to apply the aggregation logic written by user on the records. Now why it has to do sort and then why it has to do partition based on key? Because the aggregation would happen based on key only. That's why it moves the same keys or the same key ranges to same reduce node, so that the aggregate or aggregation logic can be applied on the records collectively. And then finally it is written to the HDFS distributed storage. Okay, now let's try to visualize the entire MapReduce flow. We have this input file which is on HDFS, and then on this input file the map task is run, and the map task is actually user defined. We write the transformation logic using map task, and the framework does sorting, it does merging, it also does partitioning and writes multiple output files. And then the framework copies the output files to multiple reduce nodes depending on the key ranges or key partitions. And here till this dotted line is the map phase or the mapper or map partitions. Here in the copy phase, there's a data which is getting transferred over the network, which is the copy phase. And after that, the framework sorts and merges the file based on the key values or on the key ranges. And then the user defined reduce task is run on top of it. And finally, the output is written to the distributed storage like HDFS. So instead of HDFS, it can be S3 also, both in the input file and in the output file also, output files. So this is the complete MapReduce flow, and it is very important because you'll see in future that Spark also is an extension of the MapReduce framework, but with a lot of other twists also. And if you think about Hive, if you think about any other distributed computing framework, most of them use this MapReduce framework as their base. Now here I'm showing you only one input file and one output file, how the parallel processing is achieved. So in a single node, there can be multiple map tasks running depending on the blocks and depending on the available CPUs. So let's say we have 3 cores in a particular server or in a particular node, then 3 map tasks would run on 3 different splits or 3 different HDFS blocks, which is of size 128 MB. And let's say we have 10 similar servers. Then we are achieving a parallelism of 30 because each node is running 3 map tasks and we have 10 servers. So 30 map tasks would run in parallel. And each map task could process 128 MB of data. So in parallel, we are processing 128 MB into 30, which is approximately 4 GB of data that is being processed in parallel, only with 3 cores per node and a total of 10 different nodes. So the map tasks would run in parallel across all the blocks. So would be the reduce tasks. And the number of reduce tasks can be different depending on the number of partitions. And one thing I missed in the last slide is that the partitions that are created by the map task would be dependent on the number of reduce tasks that are available. And the entire framework would actually know how many map tasks would run and how many reduce tasks are running. So depending on the number of reduce tasks running, it would create the same number of partitions. Now let's go back to this reduce phase again. Now in this case, I have 4 reduce tasks running. So that's why the map phase created 4 partitions, because the framework would know how many reduce tasks would run and how many map tasks would run. So depending on the number of reduce tasks, the number of partitions would be created by the map phase. Had there been, let's say, 8 reduce tasks running, or had there been 8 nodes and each node, let's say, was running 2 reduce tasks, in a total 16 reduce tasks. So the map phase would create 16 partitions with different key values or different key ranges. And that is the idea of map reduce, that map would read individual records, apply the transformation and generate number of partitions depending on the reduced tasks or depending on the number of reduced tasks. And then the records or the output file from the map phase would be copied over to the reduced nodes, and then the final aggregation would run, and eventually it would be written to the output file or which is in the distributed storage like HDFS or S3 or GCS. As you might notice, it would be partial output. So single folder can contain multiple number of files, multiple number of output files, and when you read from that output file, you'll have to read from the folder directly, not those individual files. So if you mention the folder, all the files inside of the folder would be written by the further map task or reduce task. One more thing is that I have shown only one map task and one reduce task. Is that the case always? The answer is obviously no. There can be multiple map reduce combination. Let's say this is the first one. So what is happening here is that the first map task is running multiple selects, let's say. Then the output is going to another map task which is running multiple different filter expressions. And then the third map task which is running multiple different data type conversions. And this is something that have been written by us developers. So that's why you have 3 different map tasks, M1, M2 and M3. The output of M1 is input to M2 and output of M2 is input to N3. And then the output of M3 is going to reduce one task, which is going to reduce 2, reduce 3, reduce 4. And all of them are running multiple aggregation logic like joining, grouping, summing, etc. Right. So this is one linear flow which can happen. Obviously, there can be a lot of other complex flow, something like this. Let's say we have 2 map tasks which can run in parallel, M1 and M2, and the output of these 2 map tasks would go to a reduced task because we are doing some aggregation. And maybe the output of the reduced task would be run in 2 different map tasks in parallel, right? And then output of map 3 would be sent to map 4, which would run reduce 2, and then there would be a final aggregation on using reduce 4 and then another map, and then the output would be given. Same is the case in the second flow also. From the reduce, it is going to one map task and then to another map task and then to a reduce task. The output of this reduce task R2 and R3 is going to R4, which is the final aggregation, and then some other map task. So there can be a very complex and combination of map reduce jobs and tasks that you can imagine. So that's what MapReduce is. It was very powerful. MapReduce framework was very, very powerful, but there was a problem. The problem was that it was only written in Java and you could only write MapReduce program using Java code. But the framework was actually meant for big data processing, wherein the DBAs or the data engineers or the data scientists work. And most of the DBAs, data engineers, etc., they do not know how to write Java code. So that's why initially MapReduce did not gain too much of traction. People had to take help of application developers to work on solving the data problem also using MapReduce framework. And then came Hive, which is a SQL-like query on top of MapReduce, and it actually exponentially increased the adoption of MapReduce framework or the big data framework or the Hadoop processing. So what happens in Hive is that there's something called Hive Query Language or HQL, which is almost similar to SQL, and SQL is something which is known by all the DBAs or data engineers or data scientists. So you write HQL, which is an SQL-like query, and it is sent to the Hive engine. And what the Hive engine would do, it would convert those SQL statements to MapReduce jobs. And then it would run using HDFS by reading the records and writing the records, just like I had shown you in the previous slide. So the Hive engine is very, very powerful in a sense that it converts an SQL statement in MapReduce jobs. So you can imagine that an entire ecosystem of SQL came into the purview of MapReduce now. And this is where MapReduce became really, really famous. And Hive is still important. It is still relevant in today's world. A lot of organizations still use Hive. Now, after the success of MapReduce, a lot of other things came also. For example, Pig, which is a scripting language for ETL that uses MapReduce under the hood, meaning that the scripting language would be converted to MapReduce jobs. Then there's something called Mahout also, which was built to create machine learning models. So it is a machine learning library. You use the library to create machine learning models, and eventually it would be converted to MapReduce jobs. So you can imagine the diversity of the MapReduce framework or the diversity of Hadoop, which works on big data. So this is where MapReduce started to gain momentum and then became really famous till the time Spark came and Spark took over the MapReduce framework. So I hope you have understood what MapReduce is and what Hadoop is. After giving the background of MapReduce, let me tell you a little bit about the big data or Hadoop ecosystem. And this is the diagram which I have taken from internet. The courtesy is Google search. I have to mention this so that I don't get into trouble. Now let's try to understand this picture. This is a very famous picture, by the way. I'll not talk about the bottommost layer, which contains Flume, Kafka, and Scoop. I'll talk about it at the end, but it starts from Hadoop HDFS. So HDFS is a distributed storage, as you already know. Right. So at the bottom, we have Hadoop HDFS, which is a distributed storage. Then there is something called Yarn, Hadoop Yarn, which is a resource management tool or a scheduler tool. We'll talk about Yarn shortly. And then we have MapReduce. So you know what MapReduce is. It's a framework wherein we write map tasks and reduce tasks, and everything else is handled by the framework. Because MapReduce was only written in Java, it was a problem. So that's where Hive was invented. And the purpose of Hive is to convert the HQL statements, which are SQL-like, to MapReduce jobs. Same is the case with Pig, which is a scripting tool for ETL. If you use the Pig Latin program to write the script, that would also be converted to MapReduce jobs. Same is the case with Mahout. And these are the only three engines that convert their native domain language to MapReduce jobs. Now everything else does not use MapReduce. Spark uses Yarn and HDFS, but it does not use MapReduce. Spark is a separate processing engine altogether, and on top of Spark we have Spark Streaming, Spark MLlib, Spark SQL, etc., which we'll anyway discuss. Then on top of HDFS there's something called Apache HBase also, which is a key value store or a NoSQL database on top of HDFS, which also does not use MapReduce. So Apache HBase works directly using HDFS or distributed storage. So it is a NoSQL database which works on distributed storage. Spark is a processing engine which works using HDFS or which works on HDFS using Yarn scheduler. We'll talk about Yarn scheduler anyway. Likewise, we have Solar, Lucene, Storm, etc. Right now, the MapReduce framework is used only by Hive, Pig, and Mahout, but the other processing engines still take help of Yarn resource management and the distributed storage. Distributed storage has to be there because there's no other way of storing big data. and the processing engine has to integrate with all the distributed storage that are available. So that's why you see the integration. Then you have Zookeeper, Cassandra, etc. Right. Now, what is this bottom layer? We have Flume, we have Kafka, we have Scoop. These are the tools to get data into HDFS. Scoop is an amalgamation of SQL and Hadoop. So using SQL statement, you can move data from relational databases to HDFS. That's what Scoop does. You can read records from relational databases like MySQL, PostgreSQL, etc. and then put it in HDFS. Kafka is a streaming ingestion. So if you have streaming data, you ingest them using Kafka and then Kafka can store them in HDFS. Same is the case with Flume also, which is a stream processing framework. So as you can imagine, a lot of things or a lot of technologies evolved out of the big data ecosystem. And we are going to learn about Spark, HDFS and Kafka, which are the most famous processing, storage and stream processing technologies today.